attendees still. I don't see myself. Oh, gotcha.
Okay, she's going to talk about the extreme topological tunability, Weyl-Kondo semimetals, Zeeman coupling.
All right. Yeah, thanks for coming to my talk. Thanks to the organizers for having me. Today I'm going to talk about some work I did in collaboration with Chimiao and Silke Pashen, and regarding extreme topological tunability of Weyl-Kondo semimetals, subject to a Zeeman coupling. Doesn't want to obey now. There we go. Okay. So by way of outlining what I want to talk about, first I'm going to introduce sort of how I'm approaching the subject of strongly correlated topological gapless phases, how I want to frame how I'm thinking about this. Then I'll introduce the Weyl-Kondo semimetal model and a corresponding cerium-based compound that has a nice correspondence with some of its signatures. And then I'll go into the extreme topological tunability aspect. Yeah, so let's get to the introduction. So here I want to think about correlations from weak to strong on this sort of spectrum. And parameterizing the correlations is the strength of the Coulomb interaction, the ratio of the Coulomb interaction to D, which is a bare conduction electron type bandwidth. And when this is, in the weakly correlated regime, if we just are focusing on topological gapless phases, there are good experimental candidates for Weyl semimetals as well as Dirac semimetals. But towards the strong end of the correlation spectrum, we still have a lot of questions. And so to approach that question, to try and get an idea of where to start in terms of materials, we can look at this figure where we plot various elements in terms of how strong the correlations are, as well as the strength of the spin-orbit interaction. So for topology, spin-orbit interaction provides energy band inversion and reordering of bands in energy. And so what we notice is that something that's a class of materials that's relatively high on both of those scales are the 4F based heavy fermions. So that's where we thought to start to look for strongly correlated topological semimetals. And so just to introduce like a basic introduction of the heavy fermion systems, you can sort of have this cartoon picture in mind where the 4F electrons are modeled as these highly localized spins, these gray spheres, the big arrows, that are stuck to the lattice sites. And that's, in terms of the Kondo lattice Hamiltonian, that's parameterized by these S vectors, and they have an interaction, usually anti-magnetic in these materials, parameterized by I, also known as the RKKY interaction. There are also conduction electrons in the system, these small red arrows that are sort of floating around the lattice, parameterized by some hopping integral. And these two species, the conduction electrons, these localized electrons, are allowed to interact via a spin-spin interaction parameterized by this JK. That's the Kondo effect that gives heavy fermion materials their characteristics. So if you put these two parameters into a ratio, you can map out a quantum phase diagram where when the RKKY interaction is sort of dominant over the Kondo interaction, you get a small Fermi surface antiferromagnetic phase where the conduction electrons are responsible for the Fermi surface and the electronic properties, and they operate in this background of an antiferromagnetically ordered phase. If you tune the parameters the other way so that the Kondo interaction is dominant, one can form heavy quasi-particles between the two species, and you end up with a large Fermi surface where these 4f electrons are contributing to the electronic properties. And somewhere in between, you can get really interesting emergent phases in this quantum critical region when these two phases are competing with one another. So that's heavy fermion systems. And then sort of separately, the particular topological semimetal phase we want to focus on are the Weyl semimetals. So when you look for topology, a topological phase, you're not looking for a traditional order parameter anymore. Usually you're looking for something to measure a topological invariant. And usually that is, the topological invariant comes from some integral of a quantity in reciprocal space we call the Berry curvature field, or kind of energy band feature, some particular low dimensional degeneracy, something like this. So in the case of the Weyl semimetal, you get pairs of band touching points, and the Berry curvature field around these points appears monopole-like. So emanating from or going into either point in K-space. And if you take your topological invariant is just an integral around a sphere enclosing the Weyl node, which is quantized, and so we seek to measure indirectly or directly in some sense this topological invariant. So how do you make a Weyl semimetal if you're thinking about this from the materials perspective? Usually in a crystal system, you have plenty of degeneracies to work with, but there are particular symmetries that will guarantee degeneracies. And then, of course, band inversion can be provided by a couple other mechanisms, but of course, spin orbit coupling is pretty reliable. And then you want to be able to control what type of degeneracy you're getting. So usually, for Weyl semimetals, you break either time reversal symmetry or inversion symmetry, and this allows you to pull apart high degeneracy into smaller degeneracies that are point degeneracies. So in principle, this is how you arrive at a Weyl semimetal. So to sort of put the heavy fermion picture and the Weyl semimetal picture together, we came up with the Weyl-Kondo semimetal model, and of course we want to put it on a particular crystal structure that's going to give us the desired properties. So we chose the diamond crystal structure, which has non-somorphic symmetries along the Cartesian axes. So here, these screw operations, these quarter turns and quarter translations along an axis bring the sites of the diamond lattice to one another. And this actually guarantees gaplessness at quarter type fillings for an odd n over 4. So quarter filling, 3/4 filling, and you get a gap state at full empty or half fillings. And so this guaranteed gaplessness you can actually reliably find on the X point in the Brion zone. And so this is an example of non-somorphic symmetry forcing gaplessness. If you add spin orbit coupling to a pretty standard diamond crystal structure model, then you can get a symmetry enforced back point at X. So towards the Weyl semimetal aspect, we choose to break inversion symmetry. So that takes you from the space group that operates in the diamond crystal structure where it's non-somorphic to the zinc blende structure, where you lose the symmetry enforcement aspect, but you still have gaplessness that's allowed by symmetry. So this is the model that we used. It's a periodic Anderson model of heavy fermions, so not quite the Kondo lattice model, but we do look at it in the Kondo limit. It has 3 parts. The conduction electrons, these represent the localized 4f electrons and a hybridization between them. The conduction electrons have a pretty standard hopping. These are inversion symmetry breaking term, parameterized by M, and our spin orbit coupling. And the localized electrons, of course, have a Coulomb interaction and a local atomic-like energy associated with them. So to treat this Coulomb interaction, we use the auxiliary boson method, where we take this Coulomb interaction to infinity and deal with the consequences of that in a self-consistent manner. So what I mean by that is we make a substitution where this auxiliary boson comes out. This essentially, because we have this infinite energy penalties assigned to 2 f electrons per site, we enforce this condition where we have 1 f electron per site plus some whole fluctuations away from that. And the size of R also defines an effective hybridization that will determine the amount of renormalization that occurs. So the sort of important aspect of like what comes out of this model and what's fascinating about the Weyl-Kondo semimetal is the contrast between when you have a Kondo effect and when you don't. So before you turn on the Kondo effect, i.e. this term is 0, you have a trivial atomic insulator. At this particular filling that we're choosing, the conduction electrons are well separated and very far away from your Fermi energy. But when you turn on the Kondo effect, what emerges are heavy Weyl-Kondo quasi-particle bands at the Fermi energy. So what the Kondo effect has done is formed the Weyl nodes, pinned them to the Fermi energy, and also, these energy bands sort of mimic the conduction electron bands, but they're highly renormalized compared to that bandwidth. These energy scales are completely different, and we think that it renormalizes to something in the Boltzmann constant times the Kondo temperature range. So, to sort of explore a couple more properties of it, we can out the surface states and the bulk dispersion around the Weyl nodes. Again, taking note of this really small energy scale that these are operating on. And we can also plot out the barrier curvature to make sure that we do have this monopole type field pattern. So we know that this is topological. So the nice thing about these barrier curvature singularities and the way that this Kondo effect pins these barrier curvature singularities to the Fermi energy means that any quantity that's associated with a singular with barrier curvature is going to be electronically accessible. And so if your barrier curvature is the dominant thing that you're trying to measure, in strongly correlated systems, this might be a way to get around other issues that you run into trying to measure topology with conventional probes. So, our collaborators came up with this cerium bismuth palladium compound, which is a Kondo semimetal in terms of transport. Of course, it has ceriums that provides the strong correlations, and it has very large spin-orbit interaction. In terms of its space group, it's non-symmorphic, so it does have some, it has the capacity for symmetry-enforced degeneracies, and it's non-center symmetric, so like our diamond crystal structure periodic Anderson model, it also breaks inversion symmetry. So they measured the specific heat, and they find this T cubed relation below the Kondo temperature. And so this makes us think that we're in a linear dispersion regime. So theoretically, if you go through the calculation of assuming a linear dispersion, you also get a T cubed relation. But if you take this enhancement factor, all these other numbers, and you compare a strongly correlated enhancement factor with, a conventional weakly correlated metal, you find that because of this reduced Weyl velocity, that you get a huge enhancement factor in this specific heat signal. So furthermore, they also looked at the Hall responses. And what they found is this giant nonlinear Hall response without any applied magnetic field below the Kondo coherence temperature. And also in the absence of any magnetism of the sample. They also found that when they do apply a magnetic field, there's both even in field and odd in field responses below the Kondo coherence temperature. So what this implies is that the transverse conductance is not coupled to any magnetic order parameter, but it is nonlinear in electric field. So serious what we think is going on is that this system is highly sensitive and it's being kicked into full non-equilibrium with a relatively small electric field. So, and what this means is that the small electric field can produce a relatively large shift in the Fermi surface surrounding a Weyl node, this Kw, and bring that Weyl node and its associated barrier curvature angularity very close to the Fermi surface, resulting in these giant responses. Okay, so now I'd like to show the sort of final results of the results that I'd like to go into about regarding the field responses. So we took our model and we added a Zeeman term to the fermions modeling our 4f electrons in the z direction. And we wanted to answer the question, can the Weyl-Kondo semimetal phase be topologically tuned before the Kondo effect disappears completely? The answer is yes. So even with this modification, the Kondo effect still forms and pins the Weyl nodes to the Fermi energy and renormalizes the bands very strongly. But we get a series of phase transitions through topologically distinct Weyl-Kondo semimetal phases before a quantum phase transition into a Kondo insulator phase. And this is just showing the kinks in these order parameters that we track across this transition. So to be more specific about what's going on in this model, so from zero field, we have this same sort of picture without any applied Zeeman field. But as you start applying it, it's a little faint, so sorry about that. But in this yellow, you can see that the locations of these Weyl nodes move inward and merge onto the X point and form a quadratic band touching. The ones that are parallel with the Zeeman field, some nodes will go towards W and some will go towards X, giving you these sort of strange nodal line dispersions when they finally meet at the XQBT points. And then if you put past that point, the nodes that have merged re-emerge on the inside of the Brillouin zone. In the XY plane, you get double Weyl fermions if you look at the local Berry curvature. And I'm not showing all of the nodes here, but they all start marching towards the zone center. And then at some point, at this LABT point, that's you get anisotropic band touching at the L point that emerge at these zone boundaries. And then they too form Weyl nodes and march towards the center at gamma, towards gamma, along with the other existing gamma X nodes. And then finally, they all simultaneously merge at the zone center, form a quadratic band touching, and annihilate into a Kondo insulator. So what we think, so the correspondence to the experiment here is, so through a combination of looking at the Hall effect, resistivity data, and torque magnetometry, came up with this phase diagram as a function of magnetic field. And what they found is a Weyl-Kondo semimetal phase that has hints of small field transitions within it due to these wiggles into a Kondo insulator-like phase. And so this is a nice correspondence between the theory experiments. And it also shows that at relatively low fields, you can get these topological transitions, and you can actually steer these Weyl nodes around the Brillouin zone without destroying the Kondo effect. Right, so to conclude, yeah, so I've shown that the heavy fermion materials are a good candidate for strongly correlated topological semimetals. They're very tunable. You don't run into the nodes are responsive to applied field, and you can get quantum phase transitions at relatively small electric and magnetic fields. Also, this incredible aspect of the Weyl-Kondo semimetals means that there are things that you can look at experimentally to try and find strongly correlated topological semimetals. And then just to sort of complete this diagram, there's also there's new proposed materials following on this design principle of combining symmetry or space group symmetry, strong correlations, and spin orbit culling to hopefully systematize how we look for topological semimetals in the future. So yeah, with that, I would like to thank my collaborators. Oops. And yeah, thank you very much for listening.
Nice talk. A comment and a question.
Sure.
Would you go back to just your summary? It's all right, no problem, no problem, no problem.
Yeah. There we go.
All right, so about point 3, right? I like that picture. I think I urged Qimiao to persuade your colleagues to carry out feedback or thermal power measurements. Anytime like this band touching, I told many of people here already, you expect to see a huge enhancement of thermal power. Very large thermal power. I understand that you guys had a paper to fight for, but I expect that even the thermal power will be dramatically enhanced. Furthermore, I expect in the compound you guys claim the spontaneous Hall effect that's large, the spontaneous Nernst effect will be even larger. Right, so I think that would be one of the opportunity if sample is more than a millimeter long, right? I talked with the other group. The sample was not in the best condition for that run yet, but you guys may have the best chance. Now, for the second point, I have a question. You see, there is no magnetism, right? is there any signatures in either nonlinear magnetic stability or there's any signatures of current-driven change of magnetic stability? So I would imagine that either there's some nonlinear effect in magnetic response, or in your idea of current-driven shifting Fermi surface, you are creating some imbalance of spin. So you should I expect magnetization start show something if you drive with the current? Anyway, that's my question.
So I don't actually know the answer to this because I'm on the theory side. I think Silke would probably know though.
Right. No.
Across the transition or?
The spontaneous Hall effect, right? It's a good thing that you see spontaneous Hall effect without magnet, right? I wonder in that case, do you see, let's say, second order magnetic stability, for example, or if you drive a current large enough, you see start to appear, see some magnet. Because even this picture, right? You drive with the current, I would expect the imbalance.
Yeah, but the current is tiny. That's not a large electric field response.
I agree.
Right? You can go to very, very small currents.
I agree.
Yeah.
Right?
But I mean, the short answer is we haven't measured second order susceptibility. Yeah.
Yes, I have a question here. Can you also tune your system to become topological Kondo insulators? Because you showed that in the end, I think it was the second part, that in the end you go to the Kondo insulator. But can you also go to topological Kondo insulator?
It's unclear at this point, like what the tuning parameter would be. I don't know if the Zeeman field alone would do that. Yeah.
And another question is that this QBT, quadratic band touching point that you arrive at it, have you tried to calculate the effective Hamiltonian at exactly that point? Does it look like a Luttinger semimetal? Is it really a 3D quadratic band touching similar to Luttinger semimetal?
So I haven't looked at the effective Hamiltonian, but I have, made a lot of plots around that point to verify from all angles that it's a quadratic band touching in 3 dimensions. I mean, that's kind of the
because it's really interesting. If it's really a 3D quadratic band touching described by Luttinger semimetal, by itself is an interesting phase.
Okay. Oh.
How numeric are
Maybe
these
just a lot
kinks in the Hall effect? How important is it to do Kondo and why? Or can you get these? Yeah. Can you get the kinks in the Hall resistivity as a function of field in Weil systems with the Zeeman term, or does it necessarily have to be Kondo Weil?
Yeah, so if you were looking at field experiments in like a weakly correlated Weil semimetal, it's very hard to actually make nodes move. There's orbital effects that come out before that point. There's broadening effects that come out, and usually the nodes will be the wave function nodes will be so broad they'll bleed into each other, hybridize and gap out. So that's because they're just operating at a much higher energy scale. So you need massive fields to be able to see anything like we see here. Because we have this high degree of renormalization, we can apply much smaller magnetic fields and preserve the integrity of the Weil nodes. Yeah. Does that answer your question? Or Silke, do you want to chip in?
I don't know whether you were asking as well whether in a non-inter or weakly interacting Weil semimetal you would have been able to see the spontaneous Hall at all, right? And I think that the answer is also no. And the reason is it is predicted to be there, but it's predicted to be tiny. So you really need to be in the situation where both the node is pinned to the Fermi energy and where you have, I think, I mean, that's not really calculated, but a very strong density of states near it, right? I mean, even though the node is pinned to the Fermi energy, you need states to produce the Hall response. And you have this very strong enhancement of density of states because the band is so flat. That's my sense why you see it so strongly there. Why this is, it's like 10 to power 4 enhanced compared to what even the most optimistic prediction in a non-interacting wire system is.
No, I'm just saying that I think that's a very good point. If you have enhancement of that, if you have such enhancement of dense states, I suspect that a small current will also lead to a large Pauli susceptibility. So in other words, your E field should drive your electrical field, small electrical field or current should create a big magnetization. And as you point out, there's a large cluster of dense states. Oh yeah, all Pauli susceptibility. Well, yeah. It's not a magnetic field. Yeah, no, I get that. All I'm saying that if that stability itself changes with a small current, that's just I'm wondering about that.
Okay, well, let's thank our speaker. Let's follow the break coming back time, right? Yeah, okay, 10:55. Yeah, thank you.
Right.
You see that slightly above, you see that